Okay, so this is the answer key for the stoichiometry practice quiz. In our first question, we're given a certain number of moles of aluminum and asked how many moles of hydrochloric acid could be produced. So this is a mole-to-mole conversion, which is the central piece of every stoichiometry problem that we're going to do. So these three boxes, the step that we see at the bottom, we're going to be doing this step in every single problem we're going to do in this quiz. But here, we're just doing this core piece. That's all we're being asked to do. So the question is, if we're given 0.87 moles of aluminum, okay, so this is aluminum. We're being asked to find HCl. It might help to label the boxes so you know which substance goes in which box. The key thing here, and the key thing in every stoichiometry problem, is your mole ratio, this center piece. If you don't get this right, you can do everything else right and still come out with the wrong answer. So the key here, two things. One, every number that goes in this middle box comes from the balanced equation and nowhere else ever. Okay, so this middle box called the mole ratio takes its numbers from the coefficients in the balanced chemical equation every single time. Never any number from the problem, never any calculation. It's right out of the balanced equation. The way you set up the mole ratio is that the thing you're trying to find, the unknown substance, the coefficient of that unknown substance goes on top. So the question is, how many moles of HCl would be needed? Sorry, I said produced, but you do it the same way. So we want to know, if we've got a certain amount of aluminum, how much HCl would it take to completely react with that amount of aluminum? So that's the question. Either way, the process is the same. The top is the coefficient of the unknown substance. The unknown is HCl in this question. So there are 6 moles of HCl. And then on the bottom of every mole ratio is the coefficient of the thing you started with. We started with aluminum. So the coefficient of aluminum is 2. Okay, so the thing you're trying to find, the coefficient goes on top. The thing you started with, the coefficient goes on the bottom. That's the mole ratio. Those numbers come from the equation. I can't say it enough, and I'll keep saying it. Okay, so what this means and what the equation tells us is that for every 2 moles of aluminum, you need 6 moles of hydrochloric acid to go with it. That's the recipe. Now, since we didn't start with 2 moles of aluminum, we have to figure out what's the proportion that will give us the right amount of hydrochloric acid. The way we do that is by multiplying the number of moles we were given by this ratio. So 0.87 times 6 over 2 is 2.61 moles of HCl. Okay, so if you start with 0.87 moles of aluminum, you need 2.61 moles of hydrochloric acid to go with it. That will give you the right ratio to complete the reaction. Okay, so we took the starting amount we were given, multiplied it by the mole ratio. That gives us the answer. That's all we need to do. But again, I want to point out that this step is going to be part of every question we answer from here on out. That core conversion of moles of the given to moles of the unknown is required, and the mole ratio is required for every single stoichiometry problem we're going to do. So let's move on. Okay, so now we're given 9.8 grams of Al2O3, aluminum oxide. And the question is, how many grams of aluminum can be created? So we're given the reactant in grams, and we're asked to find how much product we can get in grams. So if you're starting with grams and you need to end with grams, now we have we have more steps to the problem. Okay, and all we're doing is we're taking, so here's that 3-box set that we had in the first problem. This is the mole conversion step. But we have an extra piece at the beginning because we didn't get moles, we got grams. Okay, so we have to start, and I'm going to label again, the boxes here, because we're starting with Al2O3. That's what we were given. So that first box is about Al2O3. The second box is about Al2O3. And since that's what we were given, when we get to the mole ratio, we're going to put the coefficient of Al2O3 on the bottom. Whatever you're starting with goes to the bottom of the mole ratio. From there, we convert over. That's what this step, this mole ratio, converts moles of given to moles of unknown. The unknown is what you're trying to find. The question is about aluminum. So this step is the bridge between what we were given and what we're trying to find. From here on out, everything we do has to do with the unknown, which in this case is aluminum. Okay, so just labeling those boxes to give us like where we're going to look to find the answers or to find the numbers that we need. So we were given 9.8 grams of aluminum oxide. Now you need to go to the periodic table, which I don't have crammed on here, but use the periodic table to calculate the molar mass of Al2O3. So I take aluminum times 2, the molar mass of aluminum times 2, plus the molar mass of oxygen times 3. Combine that, that gives me the molar mass of the compound, which comes out to 102 grams. Right? So 9.8 grams is what we have. A mole of that would be 102 grams. So obviously we don't have a mole. We have somewhere around a tenth of a mole, which is what we're going to find. We calculate it and we get 0.096 moles of aluminum oxide. Okay, so now we've converted the grams into moles. Now we can use the mole ratio to bridge over to the unknown. We're building a bridge to the unknown here. So the coefficients, again, coming from the equation, our unknown is aluminum. The coefficient of the aluminum is 4. And then on the bottom is the coefficient of what we were given, which was the aluminum oxide. So now we multiply 0.096 times 4 over 2, which is really multiplying it times 2. Right? 4 over 2 is 2. So 0.096 times 2 is 0.192 moles of, now we're talking about aluminum. Okay, so if we start with 0.096 moles of aluminum oxide, we should be able to produce 0.192 moles of aluminum. And again, it's a 2-to-1 ratio, so we get twice as much in terms of moles. The chemical equation is always written in terms of moles. All right, now if we want the grams, because that's what the question asks, the next step, which is really the last step in this problem, is multiply the number of moles times the molar mass of aluminum. From the periodic table, aluminum has a molar mass of 27. So 0.192 times 27 is 5.18 grams. Okay, there's the answer. How many grams of aluminum can we get if we started with a little less than 10 grams of aluminum oxide? We had to convert the grams given to moles, then bridge over using the mole ratio, moles of aluminum oxide to moles of aluminum. Last step, because we want the answer in grams, is take the moles of aluminum times the molar mass, and that gives us the grams. Okay, so that's, in terms of steps in the stoichiometry problem, this is sort of the longest problem we're going to have to do. There's other little pieces that we add on in terms of what we do at the end. But in order to get the answer to a grams to grams stoichiometry problem, this is as big as they get. Right? So the next question, and you see we have the same boxes here, so we're going to be doing the same set of steps, different substances, different masses, and so on. But these are the steps we need to do for each one of the problems from here on out. Okay, so in the experiment, 40 grams of potassium chlorate is heated until it decomposes. So you heat this up and it breaks down. So that's the reaction. Decomposition reaction, one thing breaks up into two different things. What is the theoretical yield? And I'll tell you, whatever we get in that box is the theoretical yield of oxygen, which is O2. All right, so let's label our boxes so we know what we're working with. We're starting with potassium chlorate in grams. Then we'll convert that to potassium chlorate in moles. The mole ratio is going to have potassium chlorate on the bottom and oxygen on the top. That converts or transitions from talking about the potassium chlorate given to the oxygen, which is what we're trying to solve for. And at the end of it, we're going to have a certain number of grams of oxygen. Okay. We were given 40 grams of potassium chlorate. On the bottom of this box, we need the molar mass because we're converting grams to moles. That's the first step. Look it up on the periodic table. Potassium plus chlorine plus 3 oxygens, because it's O3, gives us a total of 122.5 grams. Okay, so a mole is 122. We have 40, so we're going to have roughly a third. And actually rounded, it comes out to exactly a third of a mole of potassium chlorate. So now we've got it in terms of moles. We can use the coefficients from the equations to transition from given to unknown. Okay, the coefficient of the unknown, oxygen, is 3 moles. The coefficient of the substance we were given is 2. Okay, so 1/3 times 3 over 2 gives us 0.5 moles. Okay, so for every 0.33 moles of potassium chlorate, we get a half a mole of oxygen. Multiply that, because we want our answer in grams, times the molar mass of O2. Again, look it up on the periodic table. Oxygen has a mass of 16, so O2 would have a mass of 32 grams. So we're going to take the 0.5 times 32. 0.5 times 32 is 16 grams. So if we start the reaction with 40 grams of potassium chlorate, we should produce 16 grams of oxygen gas. So that's the answer to the first question here. What's the theoretical yield? The theoretical yield is the answer you get in that last box. Okay, that's always what we call the theoretical yield. Second part of the question is, if we do this experiment and we actually collect 14.9 grams of gas, what is our percent yield? So the theoretical yield is what we should get. Okay, if we start with 40, we should get 16. But we do the experiment and we actually get a little bit less than that, 14.9 grams. So we take what we actually got, divide it by what we theoretically could have gotten according to our calculations, and then we multiply that times 100 to make percent, and we get a result of 93.1% yield. Okay, so that's the answer to the second part of the question. What is the percent yield? 93. Okay, so we take what we calculated is the theoretical, what we're given as the actual yield, divide that by the theoretical, times 100 makes percent, and that's the answer to that question. So this is the first time we have 2 substances to start with, and we're still trying to solve for how many grams of product we can get. So when we have 2 different reactants, we don't know which one we should use automatically. In the other problems, we were only given one, so we didn't have a choice. Now that we have a choice, we have to find what's called the limiting reagent or limiting reactant. And the easiest way to do this is start the reaction, start the equation once with each reactant, and carry out the calculations until you get to the transition where you know how many moles of product you're going to get. Once you reach that number, figure out which one is smaller and finish the calculation from there. Okay, because that will tell you whichever answer is smaller at that point, that calculation is going to give you the limiting reactant, and that answer in terms of grams formed will be the final answer. And I'll explain more about that as we go through it. But here's what we're going to do. We're going to start one calculation with the ethylene and one with the oxygen. Okay, so the top row is going to be starting with the C2H4, and then the bottom one is going to be starting with the oxygen. So this is C2H4, This is O2. When we get to the mole ratio, the bottom will be C2H4. The bottom here will be oxygen. In both cases, the top, or the unknown rather, is CO2. So once we get to that transition, we're talking about CO2 all the way down. We won't have to necessarily complete every step of both calculations, and I'll show you how to figure that out when we get to it. So first, we're starting with 4.95 grams of ethylene and 3.25 grams of oxygen. Now, I like to do these in parallel, kind of step by step, because when I do get to this one point, I can stop one of the calculations. You could do them both completely through and then pick the smaller answer at the end. There's nothing wrong with that. And if that's easier to track than trying to do them both side by side, do it that way. That's fine. I'm just going to show you how I would do it, but there's other ways to do this problem. So in the first boxes, we need the molar mass of each substance. So C2, that's C2H4, has a mass of 28 grams. O2, oxygen, has a mass of 32 grams. Divide the grams given by the molar mass in both cases. We get 0.18 moles of ethylene, and we get 0.1 moles of oxygen. Now to the mole ratio. Again, the mole ratio always comes from the equation, nowhere else. We're going to create two mole ratios because we're doing two different calculations. So for the C2H4 up here in the equation, the coefficient is 1, and the CO2 has a coefficient of 2. So that's a 2-to-1 ratio. For the oxygen, there's a coefficient of 3, and the coefficient of CO2 is still 2 moles. Okay, so we have a 2-to-1 ratio on the top and a 2-to-3 ratio on the bottom. So you can see the numbers are different here. When we do this calculation, we see that we would get 0.36 moles of CO2 if we start with the ethylene. Keep wanting to say acetylene. So if we multiply the 0.1 times 2/3, we get 0.067 moles of CO2. All right, so I'm going to pause right here and explain this is why I do it this way. Now we have CO2 expressed in moles, which are always comparable, for both equations. Starting with 4.95 grams of C2H4, we should get 0.36 moles of CO2. Starting with 3.25 moles of oxygen, we would get less than that, 0.067 moles of CO2. So right here, I can say for sure that this calculation down here is going to produce a smaller answer because the only step left is multiplying by the molar mass of CO2, which is the same because it's CO2 in both cases. So I'm multiplying whatever number I have here times the same number. So the proportion is going to be the same. So I can do 0.36 times 44 and I get 15.8. I do 0.067 times 44 and I get 2.95 grams. Okay, so again, you can see if I look at the final answer here, the C2H4 could create up to 15.8 grams of CO2. However, the amount of oxygen I had to begin with is only capable of creating a little less than 3 grams. So even though I could make a lot more CO2 given the amount of ethylene I started with, I can't make this much because I only have enough oxygen to make 3 grams. So the amount that I could possibly produce, which is the answer to the first question here, is 2.95. Okay, what is the limiting reactant? The limiting reactant is the thing I started with that resulted in that smaller number, which is the O2. Okay, so the oxygen by the calculation shows us that it will produce less stuff than the C2H4 did. Therefore, the oxygen is going to limit how much we can create. Because once we've created 2.95 grams of CO2, we're out of oxygen. We've used it all. We can't make any more. So even though there's going to be some ethylene left over, doesn't matter. We're done. Okay, so the other thing I wanted to show you, and again, the reason why I do this step by step in parallel, is once I get to this step, like I said, I can tell from here that the bottom one is going to be the answer I need to find. So I don't really have to do this last piece for both. I only have to carry it out from the smaller answer to get to the grams. Again, if you go through the whole thing one at a time from start to finish, you'd get the same result. You'd figure out that the second one is the smaller answer. That's the correct amount of grams you could get, and that determines the limiting reactant. There's nothing wrong with that. To be fair, it doesn't save you a whole lot of work to do it the way I showed you, and maybe doing it in parallel like that gets more confusing. It's fine. Just do one calculation all the way to the end, start over, do the second one all the way to the end, find the smaller answer, and you're done. So either way is totally fine. All right. The last question is sort of the bring it all together question here. We have two different reactants to start with. We're being asked the limiting reagent, so that part is just like the last problem we did. And then finally, we're given an actual yield of 8.52 grams and asked to find the percent. So that was 2 problems ago we did a percent. Last question was a limiting reactant. This is putting it all together, and it's grams to grams. So it's going to use all the boxes and all the sort of tricks of the trade we've used so far. So I'm going to break this down into a couple of parts. We'll go through it step by step. All right, so how many grams of NH3, which is, it's really the only product, could be produced theoretically, our theoretical yield, from 50 grams of N2 and 5 grams of H2? And you might say, well, obviously the 5 grams of H2 is going to run out first. You can't count on that because molar mass and mole ratios might make it so that actually the nitrogen runs out first. We'll see. So I'm going to run the calculation twice. I'm going to do N2 and H2. So again, this is going to be about N2, 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 and then we're trying to find NH3 in both cases. So I'm going to put NH3 down here, just again so I can keep track of which substance I'm working with in which box. On the bottom, I've got H2 here and down here. And then it transitions over to NH3 for the rest of the ride here. Okay, and that's equals here and here. Okay, now we can get to work. Top row, 50 grams of nitrogen. Bottom row, 5 grams of hydrogen. Again, if you want to do these one at a time, I'm going to do it one at a time so you can see what that looks like. All right, so we'll start with the nitrogen. We'll do that all the way through. We'll start with the hydrogen. We'll do that all the way through. That way you can see what that looks like if that's how you'd rather do it. All right, so grams of nitrogen gas. The molar mass of nitrogen is 28, which means we have roughly 1.8 rounded moles of nitrogen. The coefficients here, the coefficient of NH3 is 2. The coefficient of nitrogen is 1 mole. Okay, so 1.8 times 2 over 1, 3.6 moles. Okay, so for every 50 grams of nitrogen, we'll get 3.6 moles of ammonia. And then we multiply that times the molar mass of NH3, and we get 61.2 grams. Okay, so starting with 50 grams of nitrogen, we could produce up to 61.2 grams of NH3, ammonia. Okay, Now let's do the second equation, or second calculation, starting with hydrogen, 5 grams. The molar mass of hydrogen is, or sorry, of hydrogen is 2. So 2.5 moles. So just here, I want to show you, right? You said, oh, well, 50 grams is 10 times 5 grams. So obviously that's going to be the limiting, not going to be the limiting reactant. But look here, there's actually more moles of hydrogen in 5 grams than there are moles of nitrogen in 50 grams. So you have to kind of carry it through because it's not always as obvious as it seems. All right, so then mole ratio, the coefficient of ammonia is 2 still. That's the same for both calculations. The coefficient of hydrogen is 3. So different ratio. First one was 2 to 1, this one's 2 to 3. When we do that, we get 1.67 moles of ammonia. So 5 grams of hydrogen gas can produce 1.67 moles of ammonia. That's again times 17 grams for the molar mass of ammonia. 28.4 grams of ammonia could be produced. So we've done the calculation starting with the 50 grams of nitrogen. We did the calculation starting with the 5 grams. And yes, it does turn out that the limiting reactant is the one that we started with the smaller amount of, but that's really not always the case. If this ratio in the middle was a little different, it could be a completely different result. So you can't count on it being obvious. All right, so the limiting reactant is the one that gives us the smaller answer, so it's going to be H2. The theoretical yield is 28.4 grams. Again, what that means is we have enough hydrogen to make 28.4 grams, and then it's gone. The nitrogen, there's enough to make a lot more ammonia, but we can't make that much because we run out of hydrogen. Okay, so that means also in practical terms, there's going to be some nitrogen left over. Once all the hydrogen's used up, there's going to be a certain amount of nitrogen left over. We could calculate what that is. We don't need to go that far. And again, just for me, if you're looking at this calculation, this is the point at which you can decide which is going to be the limiting reactant. Now, you still have to finish the calculation to find how much you're going to get, but you can see right here that it's less ammonia being produced by the hydrogen than the nitrogen because the number of moles is smaller. All right, so let's finish this out. We said that the limiting reactant was the H2 because it can only produce 28.4 grams. That's the theoretical yield. How many, what's our percent yield rather? Well, our actual yield is 8.52 grams. We said our theoretical yield based on the limiting reactant is 28.4. We're going to divide that, multiply by 100 to convert it to percentage, and that comes out to 30%. Okay, so not a great yield percentage-wise, but that is what it is. Again, that number can be anything between 0 and 100. Could it theoretically be 0 if you got 0 product? Sure. Could it theoretically be 100% if you got a perfect result? Yes. Both of those are extremely unlikely. It's going to be somewhere in between. If you get more than 100%, it's wrong. Has to be wrong. You can't ever have more than 100% yield. But if it's really low, like 5%, or really high, like 98%, that's okay. That doesn't mean that it's wrong. All right, so that was one problem that brought everything together, converting grams to moles, moles using the mole ratio, finding the limiting reactant, finding the percent yield and the theoretical yield. You need to be able to do all of that stuff. The quiz will follow the same progression. There'll be a mole to mole, grams to grams, and then a limiting reactant and a percent yield question, and then one question at the end like this one that does everything all together. All right, so that will be the quiz. On the quiz, you'll get the periodic table. I didn't show it on here, but you'll use the periodic table to find the molar masses, so that'll be given to you on each page. You'll want a calculator. I'll put the boxes on the slides where you need them to do the calculation. You don't have to use them, but they're there in case you want to help keep things organized. But if you'd rather do it out by hand, that's fine. So there you go. That is the answer key for the stoichiometry practice quiz.